We now know how to find analytically what the magnitude and the gain are going to be given a transfer function for its steady state output when our input is a simple harmonic function, just a cosine or a sine function with a set frequency. Now we're going to look at a tool that we can apply in order to visualize better what happens as we change the frequency of our input. And that tool is called a Bode diagram. So a Bode diagram visualizes the magnitude and phase shift over a whole range of input frequencies. So it is just visualizing exactly the same equations we just talked about prior to this slide. But now we're going to be able to see over a whole range, is the magnitude going up or down, at what frequencies might it be the highest or the lowest, and the same thing as for the phase. Are we in phase for a certain range and then we go into anti-phase, or we're somewhere in between at this range of frequencies? So the standard way we show the Bode diagram is going to be the way that MATLAB makes it, and we just we'll look at in our forthcoming example here, but we're going to see that it's really two plots on top of each other. The top plot is going to be showing us the magnitude versus the input frequency, and then the bottom plot is going to be the phase versus the input frequency. And we're going to see that the frequency, I'll actually start at the bottom here, the frequency is going to be in log scale by default. So it's going to be 10 radians per second, 100, 1,000 as our scale. And we'll see in MATLAB how we can get our exact values out of it. And then for the top graph, the magnitude graph, we're going to see that the magnitude by default is going to be expressed in decibels. And we see here in yellow the equation for how we are going to be able to convert from one to the other. So this LDB is the level in decibels, and that's what the plot out of MATLAB is going to show us. And that is equal to 20 times the 10 log of the magnitude. Remember, the magnitude is that ratio of B over A, the output amplitude over our input amplitude. So if we want to find the magnitude and we make the Bode diagram in MATLAB, we're going to actually use the right side of this equation here. We're going to know the level in decibels. Maybe it's -10, -20, -50, whatever that is. If we take 10 and raise it to that level in decibels over 20, that will get us back the magnitude. And that's usually what we need because we're going to be wanting to find the output amplitude. So we'll be using this equation in the next example. And then the bottom plot is going to show us how the phase is going to change over the frequency range. The phase by default is going to be shown to us in degrees, but that is going to be in a linear scale. Sometimes what we'll see as we get into second order and higher systems typically is that the magnitude or the amplification is going to have a spike or maybe multiple spikes along the range of frequencies. And what this is going to mean is that if we are operating at or near that frequency with our input, we're going to have a very large output amplitude. And typically we want to not operate near these spikes. And we're going to see a little bit later different ways we might be able to remedy this, either by changing the shape of the Bode diagram, which really the only way to change it is to change the transfer function, which means we would have to change the elements of our system, springs, masses, and dampers if it's mechanical, or capacitors, inductors, and resistors if it's an electrical system. Or another option is if we can't change the system, maybe we have to change the input frequency. So again, in short, the Bode diagram is simply a visualization of how we calculate the magnitude based on the transfer function and the phase based on the transfer function. So it uses just the equations we saw on the previous slide.